In the series of lectures under the banner Statistics and Management Studies, we discussed several topics, and I hope that they reached in the minds of the students in the proper manner. Based on that confidence, in this lecture series, I introduce the topic linear programming. Programming means planning. Management studies is always related to scarcity of raw materials and unlimited requirements. Hence, planning is a must. Programming means planning. It is a part of operations research. Linear programming is a problem of planning with respect to some mathematical aspects. Linear is purely a mathematical concept. It explains a linear relationship, a straight line relationship, a rigid relationship. Programming means planning. What to be planned? In management, we have only two factors, that is profit and cost. Profit is to be maximized, although that is very simple. Produce maximum, sell maximum, then we get maximum profit. Cost is to be minimum. We do nothing. The cost is minimum. But it is not a objective, not a purpose in management studies. It is always related to some conditions. Conditions apply in all management problems. That is, we have to maximize profit or we have to minimize cost subject to some conditions. Maximum profit related to limited availability and unlimited requirement. Minimization of cost satisfying our requirements. So it is a mathematical as well as management problem, linear programming. In this lecture series, in this lecture class, I am planning to introduce formulation of a linear programming problem. Introducing the concepts of linear programming. Programming is planning and linear is a mathematical term. It is defined as a straight line relationship, moving in the same direction or moving in the opposite direction in a straight line. So that is linear programming. It is a part of management decision problem and it is a branch of operations research. Then what is the purpose of linear programming? It is a problem of optimization to derive the best, to attain the best. In management studies, we have two components, profit and cost. Therefore, linear programming is used to derive maximization of profit or minimization of cost. So what is the problem of maximization of profit? Profit maximization is based on or related to some conditions, some constraints. Similarly, minimization of cost also. They are not independent. They are dependent. They depend on several factors. So, linear programming is a problem of optimization. That is, maximization of profit or minimization of cost. These are the two usual objectives of linear programming. So, that's an objective. Our objective is to optimize. It's a problem of optimization. So, what is the condition for this? As we know, in economics, in management studies, we need two factors. What are they? One is availability of raw materials. Availability. So one factor is availability. Availability is always restricted. Scarcity of availability. If there is no scarcity, then there is no management studies. There is no economics. There is no commerce. So availability is always restricted. That is the term scarcity. Then what about requirement? The requirements are unlimited. The availability is restricted and requirements are unlimited. So linear programming is problem of management decision, it's a problem of optimization subject to availability and requirement, subject to limited availability and unlimited requirement. This is the limited and unlimited. Availability is limited. So these two factors. So what is the next step? What is the next definition? Linear programming is a problem of optimization subject to conditions, subject to conditions. So it is known as linear programming is a problem of constrained optimization, either maximization or minimization subject to conditions. Then we are introducing the mathematical formulation of linear programming. A linear programming is a problem. So it is called linear programming problem or LPP. It has two stages, two phases. One is formulation of LPP and solution of LPP. And formulation is based on mathematical concepts. So it is called mathematical formulation. What is our objective? We have to maximize profit. We have to minimize cost. That is, something is to be decided. They are called variables. They are denoted by variables. They are called variables denoted by x1, x2, etc. If these variables are to be decided, so the first component is decision variables. The variables are to be decided. So that is the first component of a linear programming problem. Definition of the decision variables which are to be decided. That is decision variables. For what purpose we decide? We have an objective. So decision variables is used for attaining the optimum of a function known as objective function. So objective function is a simple mathematical statement: maximize the profit or minimize the cost. How will you maximize? That is subject to some conditions. That conditions are known as constraints. Constraints. They are the conditions, constraints. In mathematical terminology, we use equal to, or less than or equal to, or greater than or equal to, depending on the problem, depending on the availability and requirement conditions. And in real life situation, we never use negative concepts. That means all variables x1, x2, etc., xn are always greater than or equal to 0. That is, in the formulation of a linear programming problem, we have 4 components. One is decision variables. That is a mathematical terminology variable which vary in magnitude and direction, denoted by x1, x2 or xy, etc. Then our objective is to decide or suggest values for the variables such that the profit is maximum or cost is minimum. So the first component is definition of the decision variables. For example, in a profit maximization problem, the unit profit of each component is known, is given. Then how much is to be produced for maximizing profit? Each component, how much is to be produced, that is to be decided. That is the decision variables. That is the first component in the formulation of a linear programming problem. And 2, how will we decide the values? We have a purpose. It is known as objective function. That is again a mathematical function. For example, in the case of a profit function, the maximization of profit denoted by Z. That's a mathematical notation. Z is given by or expressed as C1x plus C2y, where x and y are the variables whose values are to be decided, and C1 and C2 are the profit coefficients. Usually they are known. So the objective function is a linear function of the form maximize Z equal to C1x plus C2y. If there is no restriction about availability of materials, our problem is culminating here. Maximize profit. Put x equal to infinity. Put y is equal to infinity. We get infinite profit, but it is not possible in a management decision problem. Then comes the third component, linear constraints. Constraints means some mathematical statements giving relationship between availability and requirement. Mathematical statement, availability and requirement, they are connected by equal to, less than or equal to, or greater than or equal to, according to the objective of the problem, according to availability and requirement conditions. And finally, the fourth one, in a real life situation, we have no scope for negative space. All the variables should be positive. That is the non-negativity conditions. Hence, for a linear programming problem, in the stage of formulation, we have to consider 4 items, 4 components: decision variables, objective function, linear constraints, and non-negativity conditions. Let us see with respect to a problem. A problem of formulation is discussing now. A company manufactures 2 products A and B. 2 products A and B. The profit per unit product of A and B are rupees 30 and rupees 40 respectively. Availability and requirements sources are given. Requirement, product A, product B, and availability. Which are the requirements? Raw material is needed. Machine hours is needed. Assembly hours is needed. 3 components: raw material, machine hours, and assembly hours. Then product A, it requires 60 hours, 8 hours, and 3. 120 kilograms, 5 hours, and 4 hours. And availability. So what is our problem? The problem is of maximizing the profit. Profit is to be maximized. So what is to be decided? Decision variable. How much of A, how much of B is to be produced? That is our objective. That is our decision variables. We define X and Y are the number of units of A and B to be produced. And the profit is 30 and 40. Let X be the number of units of A to be produced and Y be the number of units of B to be produced. And the unit profit is 30 and 40. Therefore, the profit is 30x plus 40y. From X units of A, Y units of B, we expect 30x plus 40y. That is how many rupees. And it is to be maximum. And we exhibit as maximize Z equal to 30x plus 40y. That is the objective function of the problem. Objective function. Suppose there is no restrictions on availability and requirement conditions. We get infinite rupees of profit. How? Produce infinite number of units of A, infinite number of units of B. We get infinite rupees of profit. But it is not possible since we have some availability and requirement conditions. Let us formulate that linear constraints. One about raw material. One constraint about raw material. That is 60 kilograms of raw material for 1 unit of product A is required. 120 kilograms. So that is 60x plus 120y. This is so many rupees. This is so many kilograms of raw material. And that is the requirement. What about availability? 12,000. 12,000 kilograms is available. That means we can use up to 12,000. A single point more than 12,000 cannot be used. So that is either equal to or less than. That depends on the condition. We never use more than 12,000 since the availability is 12,000 kilograms of raw material in kilograms. 60x plus 120y is less than or equal to 12,000. That is the first constraint related to the raw material. Second one is machine hours. Second constraint is machine hours. That is 8 hours for unit product A is required. 5 hours for product B is required. That is 8x plus 5y. What is the availability? 630. 630. We cannot use a single minute more than 630. We may use 630, but it is never more than. So that is equal to or less than. So this is so many rupees. This is so many kilograms. This is so many hours. And the third one is assembly hours. Assembly hours. That is 3x plus 4y. That is the requirement. And availability is 500. That is less than or equal to. What about the last component? Non-negativity conditions. We never produce negative number of units. Either 0, no production, or more than. That is x is always greater than or equal to 0 and y is always greater than or equal to 0. Then we get the 4 components. The first component and these three constitute the linear constraints, availability, requirement conditions, and this is the non-negativity conditions, the 3 components. And the first one is definition of the decision variables. So the problem is, our problem is reduced into a mathematical problem. That is, the 3 components are maximize. That is the objective function, maximize. Z is equal to 30x plus 40y. That is the objective function. How will you achieve it with respect to constraints? 60x plus 120y less than or equal to 12,000. 8x plus 5y less than or equal to 630. 3x plus 4y less than or equal to 500. Mathematically identical statements, but they are significantly different. This is raw material, machine hours, assembly hours, and one more. Always x and y, non-negative variables, x and y greater than or equal to 0. This is the formulation of a linear programming problem. So what is meant by linear? All these relationships are linear, straight line relationship. So this is a formulation of a linear programming problem with respect to maximization. This is another linear programming problem. And the question is to formulate. It is given that there are 2 foodstuffs, namely A and B. And their costs are rupees 6 and rupees 8 per gram. And finally, our objective is to minimize the cost. Minimize. This is a problem of minimization. Very conveniently, we can minimize it without buying 0 units of A, 0 units of B. The cost is 0. But that is not a management decision problem. And one more information is there. A food A contains 2 types of vitamins, B1, B2, and per gram it contains 20 units of vitamin B1 40 units of vitamin B2. From food B per gram, 30 units of vitamin B1 and 30 units of vitamin B2 are available. But one more, the minimum requirement of vitamins are 900 and 1200. That is, we have to formulate a problem to minimize that cost of foodstuffs subject to satisfying these requirements. So the problem is formulate LPP so as to minimize the cost such that the requirements are satisfied. Our requirements are to be satisfied. This is a problem of linear programming, and the objective is to minimize. So what is to be decided? How much A is to be purchased, how much B is to be purchased. That is the decision variable. Let us decide. Let X1 be the number of units of A to be purchased and X2 be the number of units of B to be purchased. A and B are the foodstuffs and X1 and X2 are the decision variables. How much is to be purchased? X1 and X2. What is the objective function? Cost. 6x1 plus 8x2 is the required cost. 6x1 plus 8x2 is the required cost for x1 units of A and x2 units of B. It is to be minimum. Therefore, the objective function is minimize. The usual notation is Z equal to 6x1 plus 8x2. At this stage, it is so simple. Put x1 equal to 0, put x2 is equal to 0. The cost is 0. The minimum cost is 0. But our requirement is not satisfied. Then we are going for linear constraints. The first one is about vitamin B1. Vitamin B1. 20 units of vitamin B1 is available. That is from foodstuff A. 20x1. How many A? X1A. Therefore, we get 20 x1 units of vitamin A from food A plus 30 x2 from food B. About vitamin B1. And the minimum requirement is 900. Minimum requirement. Minimum. That is the important terminology. Minimum. That is, it never less than 900. If it is more than 900, no problem. So the condition is greater than or equal to. That is the point to be noted. That is greater than or equal to. And with respect to vitamin B2, what about the availability? 40x1 from food A, 40x1 from food A plus 30x2 from food B. That is the vitamin B2, 40x1 plus 30x2, and it is 1200. The minimum requirement is that should be more than, should not be less than, that is greater than or equal to. There are two conditions in this problem. Therefore, we have two constraints. The number of constraints is equal to the number of conditions, and x1 never be negative, x2 never be negative. So this constitute the formulation of linear programming problem. This is only formulation. We have to solve for it. For solution we use another method, graphical method or simplex method. This is the stage of formulation of a linear programming problem. This problem is presented in a nutshell as, what is our problem? Minimize. Which is to be minimized? An objective function. How will you notate? Z. Therefore the problem is minimize. Minimize Z equal to 6x1 plus 8x2. How will you minimize this? Subject to the conditions. Subject to conditions or such that. We use both terminology. Subject to the condition or such that 20x1 plus 30x2 greater than or equal to 900. What is the difference? This is in so many rupees. This is in so many units of vitamin B1. And this is 40x1 plus 30x2. So many units of vitamin B2, which is never be less than 1200. And x1, x2 greater than or equal to 0. This is the formulation of linear programming problem. A linear programming problem has two phases, formulation and solution. Formulation has four components: objective, first decision variables, objective function, linear constraints, non-negativity conditions. Decision variables whose values are to be decided. That is the most important thing. How will you decide with respect to an objective? How will you achieve this objective with respect to availability and requirement conditions? When you solve this from mathematical point of view, the variables, consider only the positive solutions of the variables. That is, decision variables, objective function, linear constraints, and non-negativity conditions. Now, we discussed two problems. One is a problem of minimization, other is a problem of maximization under knowledge category. Simple, direct problem under knowledge category. Then we are going for formulation. A linear programming problem in two variables can be solved graphically. If it is more than two variables, it cannot be solved graphically. In that situation, we use the method, simplex method, that we discussed earlier in a lecture class, simplex method. Now, we are arriving at one more culmination point. Here we discussed today the formulation of a linear programming problem. It consisting of four phases: definition of decision variables, definition of objective function, representing availability requirement conditions using some mathematical inequalities or equalities, and a mathematical property: all the variables should be positive. That should be a real life variable. In the next lecture series, I wish to introduce the formulation of a linear programming problem by graphical methods. Okay, thank you.